never unique. But the moment you bring in the initial conditions, they become unique. Okay. So we have now 4 conditions. We have the 2 initial conditions, and we have the 2 continuity conditions. But we have 6 parameters, right? Alpha, beta, A, B, C, D. So the 6 parameters. Still it seems like this is not going to work out very well. But we are going to see that there are some additional conditions that will be built in here. So let's keep pushing on. Basically, the point is that there will be some piece in here which is exactly like alpha and beta. So we can put that into that. And we will try to do this very at a very general level. Any questions at this stage before I proceed? Okay. So we have G of T comma T prime is equal to A times e raised to I omega naught t plus B times e raised to minus I omega naught t. This is for t less than t prime, and this is or t greater than t prime. Correct? That's it, two solutions. And we have to, at least at the stage of Green's function, we have our initial conditions too. But
it looks like you have t prime greater than t prime, I think.
Let's take this. So it's t greater than t prime, right? Yeah. T less than t prime, t greater than t prime. Right? Again, helps to have a picture. So that's your time t, and that's your t prime. So solution on the left hand side, solution on the or solution in the past, if you call t prime as your present, solution in the past, and solution in the future. There are 2 boundary conditions, and that is that G at, when you evaluate this at t prime plus delta and t prime minus of t prime minus delta t prime is equal to 0. That's continuity condition. And the derivative evaluated, this is derivative evaluated, what do you write this? Let me write G dot, right? The G dot here, the temporary equation, so that's t prime plus delta comma t prime minus of t prime minus delta t prime is equal to -1, right? That's your boundary conditions. So that's your 2 boundary conditions. So at least 2 of them we can get rid of. So let's do that. So let's explicitly solve for this. So I substitute them here, right? So this is A. When I subtract, there is an A minus C, and I'm evaluating the time t has to be replaced with t prime. So this is e raised to I omega naught t prime plus B minus D times e raised to minus I omega naught t prime is equal to 0. That's my first equation. Second equation, I need the derivative of that. So let me write this derivative here. G dot is equal to I omega naught times A e raised to I omega naught minus I omega naught B times e raised to minus I omega naught. And this is I omega naught C. And this is minus I omega naught t times e raised to minus I omega naught. Again, I have to subtract this.
Oh,
Oh, I made a
shouldn't that
mistake.
be a plus
Plus.
since you took the derivative? Then that minus sign would come down.
Here,
Am I
right?
wrong?
Here?
Yeah.
Yeah, that's the minus sign.
Okay, I see. My fault.
Right? Not this. Right?
Yes.
Yeah, go ahead. Is that clear?
Yes, that's clear. For some reason, I was thinking the first equation was minus, but it was plus.
Yeah. I think maybe you saw this. But I did make a mistake here that I was subtracting the t plus from the minus. So it should be c minus a and d minus b. Right? So I subtracted the plus quantity. So t plus delta is here and t minus delta is there. So it is c minus a, which doesn't actually matter because this is 0. Right? So in principle, it's okay. But it helps because the next one, it does matter. Okay, so now I have to subtract the plus solution, which is the plus solution is here. Subtract it from the first one. So this is c minus a times I omega naught times e raised to I omega naught t prime. And then next one is d minus v with a minus sign. And there is an I omega naught there on both sides. So I'll put that on the right side. Okay, is that clear? So that's two equations, and at least there are 4 unknowns, but at least they come in combination. Right. So that's gives me a solution c minus a is equal to find the, let's do the denominator, like this is a determinant solution we can do. The denominator will be this times this, the e raised to I omega t minus omega t, that's just 1. But that's with a minus sign, so that's a minus 1, and that is a minus 1. So that's minus 2 in the denominator. This is the determinant solution I'm trying to do. Then c minus a will be, I replace this down there, right? So this is 0 times this minus of minus I omega, so that's 1 over I omega naught times e raised to minus I omega naught. Use your favorite way of solving this. It doesn't matter, but the solution comes out apparently to be minus 1 over 2I omega naught times e raised to minus I omega naught t prime. Okay. And the next term is d minus b. Is again the denominator stays the same, so it's minus 2. And the numerator is this times this, correct? So it is minus I omega naught times e raised to I omega naught t prime. That's equal to plus 1 over 2I omega. I think that's what it is. Okay. Correct me if you see, if anyone of you is checking on this. Okay, so that's your solution for at least a combination of the parameters. So I can substitute this in there, right? So that means I can substitute c, right? C is equal to a plus this, correct. So let me substitute that in there.
So this, when you add them together, it looks like a 1 over omega naught, like a sine.
Yes, yes, that's a good point. That's what actually later on it will come out to be. But no point in adding at this point, right? Because we have substitute that in there. But you have a good point that yes, it will, that feature, it will be in terms of sine and cosines. In fact, we will find a complete set of solutions because we have an arbitrariness in the solutions, A, B. There are two more to find, correct? Okay, yeah, but good observation, yes. Okay. So I substitute the C value, which is A plus something. Right. So my solution is G T comma T prime is equal to, the first one I keep it as it is, A I omega naught T plus B e raised to minus I omega naught T. But the second one, I substitute C from here. That is, when I solve for C, that is an A plus something. So A, I write it as it is. So this is A e raised to I omega naught T. And D also has D in it. So this is B times e raised to minus I omega naught T. But then there is this actual solutions coming in. Substitute that in there. So this is minus 1 over 2I omega naught. Right, that's your C value, which is e raised to, so this is I omega naught T minus T prime, right? That's the first piece, then I put it in there. And the D is plus 1 over 2I omega naught. And this is e raised to minus I omega naught. So that's just T plus help here. So this is minus of T is minus. So this is T minus T prime. Yes.
So I must have missed a step. Can you explain to me how the minus has changed again? On e to the minus omega naught T prime. For the first term, you have a positive, and that represents A.
Where are you pointing to?
Up top when you're defining, you put minus 1 over 2 omega naught e to the positive I.
Okay, so let's do that here. So that is C, right? So remember, C is equal to A minus 2I omega naught times e raised to minus I omega naught T prime, and D is equal to B plus 2I omega naught times e raised to I omega naught T prime. Substitute this in there. So C will be A.
Okay.
Right?
Yeah, I got you now.
Omega naught T prime times e raised to I omega naught T plus D is B plus 1 over 2I omega naught e raised to I omega naught T prime, and that is e raised to my omega naught T. And this, I think, gives you the top one. So this is A, right, B, and then this is the, so let's see if I made a mistake. So no, this is correct, and this one is minus I omega T. Yes, correct. That's how it comes. So once that's clear, we can now see the solution in here. So notice this is for T less than T prime, and this is for T greater than T prime. Right? And there is one piece which is always there, which is actually homogeneous solution. So I can write this solution as, first of all, so let's write this as A e raised to I omega naught T plus B e raised to minus I omega naught T. this piece of the solution survives only on the part when t is greater than t prime. So I put a step function there. Remember discontinuity, right? Green's function has to have discontinuity, some kind of discontinuity. So this is survives only when t prime, right? And whatever this is, I'll write that as, how can I write this? Let me pull out a 2i omega or minus, let's say minus, and that is a 2i omega naught. Actually, 2i is helpful there. And this is e raised to I omega naught t minus t prime minus e raised to minus I omega naught t minus t prime divided by 2i. And as Jordan pointed out, that's actually a sine function. So our general solution here is A times e raised to I omega naught plus B times e raised to I omega naught minus 1 over omega naught times theta t minus t prime times sine of omega naught t minus t prime. Okay, that's nice. So the arbitrariness is still there. There is an A plus B. But remember that this is actually a solution to homogeneous differential equation. So this is a homogeneous solution, if I had to call that, right? A solution to homogeneous differential equation. And this is actually a particular solution. So this will be then a particular solution. Now, it may not be very obvious that is this really a particular solution? How do you verify that? Put it back into the differential equation and actually verify that this is a solution. So let's do that. Yeah, before that, let me complete this argument that I can always drop a solution which is homogeneous in completely homogeneous, because if I even were to include this, this will go back and join the first term, right? Alpha and beta that I introduced in the first part, in the first board there, it will add on to that. So we don't have to keep this in there. So a particular, we are always interested in a particular Green's function. So this one will be called, I don't know what it is called. So this is sine omega naught t. I think this is a retarded Green's function. So this is retarded Green's. So this is t, comma t prime. R stands for retarded. Now you're right in the point that, I mean, if I had not solved for C and D, instead I had solved for A and B, I would have got a different solution. Yes, that's correct. You would have got a different solution, and that's perfectly fine because Green's function are particular solutions. Particular solutions are always off by a homogeneous part. And if you had solved for C and D, there is another combination you can get. That's called the advanced Green's function. So A stands for, so let me actually look and write it down here. Okay, let's see. Yes, so this is indeed the retarded Green's function. This is also a solution. If I A and B, so then this will be plus 1 over I omega naught theta of T prime minus T. And this will be sine of omega naught T minus T prime. Right. Notice the difference is in the where it is surviving. This is called advanced Green's function. Okay. There are various other combinations. You could have done A and C, right? So if you had done that, you would have got this is T comma T prime. This is minus 1 over 2I or omega naught 2I. And this time it is mixed, right? The exponentials actually does not lead to a sine function. This is T minus T prime times e raised to I omega naught T minus T prime plus and this is F stands for Feynman. Green's function. And if you had done the other combination, you have 4 combinations that you can solve for in this case, right? So that's W T comma T prime. Minus of T prime minus T minus of and W stands for Wheeler. It was Feynman and Wheeler who first time saw this different forms of different ways you can actually build it. It seems like this is the future is coming into and affecting the past, but this is only a description actually. In fact, these are not the only 4 possibilities. There are infinite sets there, and in general, any linear combination of these 2 are also solutions. As far as you put some like whatever the initial 3, if you put 3 pieces of this and 2 minus 2 of this, as far as the total is 1, that's perfectly fine. So there's an infinite set of them, but we can put that. I'll just mention that and let's not get into the details. So as far as we are concerned, we can pick any one of them. So let's pick the retarded Green's function. And in your homework, you have to actually do the advanced one also, like you do something with your advanced Green's function and verify that this is actually a solution. Okay. So with that, now we have our Green's function. And still we have to go back and put it on our initial condition, right? So we have our Green's function, G, which is a particular solution, and that is minus 1 over omega naught prime minus sine that's one particular solution. And then our solution itself is alpha times e raised to I omega naught t plus beta times e raised to minus I omega naught t plus minus infinity to plus infinity dt prime. Now g of r t comma t prime times your a of t prime. where you have to substitute this in there. We'll come to that view and with initial conditions, right? With this is our summary, if you want, with x of 0 is equal to x naught and v of 0 is equal to v naught. So that's your summary. We still have to find alpha and beta in terms of this. That's relatively simpler, but still not complete in the sense that it gets into here also. So we have to pull something from here. We'll come to that, but in the last few minutes I have, let me actually show you that actually the retarded Green's function we have is actually a solution to your differential equation. It's always good to verify that. And this shows up in your homework also. So let's actually verify that this satisfies the differential equation. That means to say that let's start with the left-hand side of your differential equation and calculate this. We want to check that this indeed is actually, this should give you a delta function. That's a point. And let's start with Green's function and take the first derivative. The d by dt of g of r is equal. There are two places it hits. So when it hits the step function, I get a delta function. That's nice. Right? That seems to be the solution there, right? So that's sine of omega naught times t minus t prime. And then I can hit the other piece also, right? So this is minus of so when I hit this, I get a cosine omega naught t. So omega naught cancels out. Plus t minus t prime times derivative of sine is cosine. Right? Okay, that's good, but I have to take a second derivative, right? So second derivative of the retarded Green's function. That seems to make this a derivative of a Green's function. That's not pleasant. This is 1 over omega naught. So I have 4 pieces I have to hit. 1, 2, 3, 4 places I can hit. Let me write this as derivative of delta function, t minus t prime, and sine itself. Or I can hit this, which will make this a cosine, omega naught cancels. So that's delta of t minus t prime times cosine of omega naught t minus t prime. I can hit here, this place, which is minus of delta function t minus t prime times cosine of omega naught t minus t prime. And finally, I hit the derivative of cosine, which is minus, that makes it a plus theta t minus t prime. And then there is an omega naught also survives there. So there is a plus omega naught comes in, and this is sine of omega naught t minus t prime. When I multiply a delta function with something, I can set t equal to t prime. The argument of that can be set to that. So this is equal to actually 1. Right? When t is equal to t prime, this is actually equal to 1. That's also equal to 1. So second derivative of this, and this is your Green's function, right? This is actually your, if I put in a minus 1 over omega naught square, that's your Green's function. So there seems to be some feature in here, right? So this is second derivative of the retarded Green's function is equal to this quantity in here, whatever that means, the derivative of a delta function. Let me write that as let me write that as sine omega naught t minus t prime divided by omega naught times t minus t prime, and then multiply it with the t minus t prime times derivative of t minus t prime. This is sine x over x structure, right? In the limit t minus t prime, that goes to 1. So that's the reason I put it like that. That is a minus, I can write it here. That's minus 2 times delta function t minus t prime. And this piece here can be written as minus that. So it's a minus omega naught square times g up. Actually, I want to write it on the space here. That's minus okay. So we are supposed to satisfy the differential equation. If I put it onto the left, multiply by overall negative sign. So this is second derivative plus omega naught square times g of r t comma t prime. Derivative of a delta function also survives only at t equal to t prime. So in the limit t minus t prime, this is actually equal to 1. But this doesn't give me a delta function. This gives me something else. Right? This is t minus t prime. So not minus, so this is plus actually, because I overall take a sign. Okay. So we are off from the right hand side, but then one has to be very careful here. You try to show that this is actually a delta function. So let's call this is not a delta function, but let me analyze what is this. And this is also part of your solution. So let's actually evaluate this under an integral. So there is an x times d by dx of delta function and some function, some arbitrary function f of x, which is continuous. Differentiate by parts gives me x d by dx. Okay. And then there is x times delta function times f of x. And I had to operate it on the rest of the pieces. So that is dx times delta function times derivative of x and the function f. This survives only on the boundary, but on the boundary, delta function goes to 0. So this is actually 0. This whole piece is 0. Why? This again survives only on the boundary, but whenever it is on the boundary, the delta function is 0 because delta function is surviving only at x equal to 0. So this piece does not survive at x equal to infinity and x equal to minus infinity. Here, there are two pieces. That's minus infinity to plus infinity, dx times delta x. So this is a function itself if I operate it on x, or this is plus x times d by dx. This is equal to minus of f of x. Right, first one. The second one is 0 because x is equal to 0. So this actually acts like a negative of a delta function. Remember, if I ever integrate something and get back the function, that's sort of a definition of a delta function. So you argue that this actually is equal to negative delta function. So this is a negative, this behaves like a negative delta function. So on the right hand side, the two pieces that we have, 2 times the delta function, and the second one, this is seems like this is more singular than the delta function, but it is multiplied by something that goes to 0, right? So they compensate in such a way that it is still again a delta function. So this is equal to actually a delta function, and very fine calculation, very sensitive. So this is where things can go really wrong if you're not really careful, or if we overdo what this can do for you. And this all are pieces of your homework. Right? So you have to show this in your homework, and you have to do something with your advanced Green's function also in your homework. And next time, after the exam, we'll come back and show how this boundary conditions fits in to this and what is the actual general solution. Okay. Thank
So
you.
when you drew the graph for the derivative of the delta function, you drew it as a positive hump and then a negative hump.
Yes.
Are those still, is that an infinite positive spike and an infinite negative spike? It's not. Okay.
That's correct. So typically, I mean, that's a visual way of doing it. So if you have a step function, that's your step function as this, and delta function will be like this, right? So this means that this goes to infinity and this is squeezed to infinitely thin point. And a derivative of a delta function will be, you go once and then comes down. And you can think of this as a slope. It goes to 0, right? And then it goes up, goes all the way to infinity, right? And then right when it is bending on the top, it comes to 0 again, right? So that's this point. So imagine the slope there, and you can say, argue that that's this, and you can keep doing that for double prime and so on. Right? So this will be like this, correct? So that will be your double prime. But all these are 0 everywhere except x equal to 0. These are really, so these are called the singular of nature of the function. So singularities can be classified into these kinds. If you want, this is a monopole. Right? No, this is a monopole. This is a dipole. This is a quadrupole, and so on. Okay, so these are singularities classified using the idea of monopole, dipole, and so on. And the dipole actually is this. I mean, this was done by, I think this was done by Maxwell, maybe it was done by Kelvin and Tate before, because they were, in those days, in 1850s, they were actually wanting to classify all these atoms. They were wanting to interpret it as knots. Like they, at that time, the atomic model was still not there. So they were trying to classify the properties of all the atoms that's around using what are called knots in mathematical topology, right? So and for that purpose, I think they were building this. But I saw it in Maxwell readings, but there's a good chance that it's there before.
So when you integrate the delta function, the area becomes 1. When you integrate the derivative of the delta function, the area is, can you do that? Is
not 1, I think it is, in this case it is 0, I think.
Yeah, that case. So I was saying the original delta function is 1 once you integrate Right, and then when you integrate the derivative, you get 0.
This one is
And-
0.
Yeah, and
This
then that one would be 1 again.
Probably, but check on that, okay? Basically, you do the same analysis. Let me not say anything which might be wrong, right? It seems like it will survive, right? Or these are actually total derivatives, right? No, it won't survive. It will all be 0 because the x of these are derivatives, right? So this is the d square by dx square of delta function, correct? This is a total derivative, so this will survive only on the boundary, but on the boundary, the delta function doesn't survive, right? Plus infinity and minus infinity. So they are all zeros. Like only the monopole survives.
Okay.
Yeah. At least in the integral sense. But that doesn't mean that they are not, that singularity is not there. That singularity has to be dealt with.
It's very odd.
Yeah, that's what it is. I think you have to feed this in. See, that's what you have to multiply something into it to get something out. Right? That's the idea. Right? Delta function, you don't need to multiply anything, but this one you need to cancel that divergence somehow. It's a stronger divergence. So if you want to catch something, you have to multiply that high number there. Think about it. Yeah, let me not say anything. Okay.
Okay,
Okay, good. Thank you.
thank you.
Thank you.
Bye, Elia.
Thank you.
Bye,
Bye-bye.
Michael. Yeah, might have some catch up to do. Huh?
Yeah, I got way behind.
Yeah, it's not, and it won't be very comfortable to do that either. You will be still in that mood, right?
Exactly. Yeah.
Okay.
But
Bye.
I'm
Do what?
working.
Yeah. Don't worry.
Okay. See you later.
Yeah, take care, Michael.